if both of them are 0, it's up for grabs. It requires further analysis. You have to think about like limiting procedures approaching the point to figure out what's going on actually. But this one, I'm not sure how to describe it. I mean, what is this thing? I mean, if t was 1, it'd be a circle, right? So the way I think of that is it's essentially and let's keep things relatively simple. Let's suppose that t is greater than or equal to 0, right? So if t is greater than or equal to 0, when I put in 0, I'm here. That's just the terminal point, right? Put in t equals to pi over 2, where are you? Pi over 4. T equals to pi over 4, where am I? I'm at like pi over 4 times root 2, comma pi over 4 root 2. So I'm like out here somewhere. When I get to pi over 2, I'm at x equals to 0 and y equals to pi over 2. So I'm like up here somewhere. When I put in pi, y is equal to 0 and x is minus pi. So I'm like double, like over here. So this thing, it's a spiral, and it's getting bigger and bigger and bigger as you go out. But you can start to almost see that there's got to be like that vertical tangent in here, which we could find precisely where it is. What was my vertical tangents? The t, right? You can kind of see that. See, it's coming before pi. This is pi over 2. Right? You can even start to see it making sense that that's before pi over 2. So if I did this better, it would be kind of, well, anyway. And you can see the horizontal tangent, it's in here somewhere. Apparently, the horizontal tangent is a little bit past pi over 2. Not too far, though. And you can make that precise. So if I did this better, it wouldn't be a horizontal tangent right there. It's like the horizontal tangent's up here somewhere. It's a little bit past where it crosses the axis. Up here is where the horizontal tangent is. And so forth. So my larger comment here is you can use the existence of horizontal and vertical tangents to help you in graphing parametrized curves, right? All right. So I hope that I've showed you enough that if I ask you to find the tangent line to a parametrized curve, you can do it, right? It's pretty straightforward. All you got to do is differentiate them, right? Plug in the appropriate parameter and construct the tangent line. Or construct the appropriate Cartesian tangent line. Parameterized tangent line, Cartesian tangent line. These are choices that we have. So there's that. Do I have 10 minutes? 7? 7 minutes. All right. It's going to be tough. So suppose you got a curve. Like so. All right. And you got a parameterization of the curve. So any point you pick on here, we can describe it by x of t comma y of t. Right? If you wanted to calculate the length of that curve, how would you do it? See, what you should do is you should break it up into little line segments, right? And to keep things relatively simple, I'll assume that the time between the line segments is sort of equally spaced, right? So this would be time 0. This would be time 1. Let's suppose that this is for t0 less than or equal to t less than or equal to t1. right? And then, so I'm assuming that these joining points are, you know, this is like t naught, this is at t naught plus delta t, right? And let's suppose that the jth time interval is at t naught plus j delta t, where delta t is t1 minus t naught divided by the number of connecting line segments. So what's the, you know, if you focus your attention in here on one of these little line segments, so the start of the line segment would be at x of tj, y of tj, and the end of it would be at x of tj plus 1, y of tj plus 1. What's the length of that line segment? You just need to look at the, like the delta x, right? And the delta y. So the length, if I call this length L sub j, well, L sub j should just be equal to the square root of delta x. I guess I could put a sub j on here. Why not? Let's get nuts. Delta sub yj squared plus delta sub, well, delta xj squared plus delta y sub j squared, right? This is the Pythagorean theorem. But that is equal to the square root of what? Of x sub tj plus 1 minus x sub tj, right? And I don't know, why don't we divide this by, well, I'll tell you, I'll behave. That's squared plus y of tj plus 1 minus y of tj, that quantity squared, right? This is just an expression for the length of the jth line segment approximating the length of the curve. But the thing is, we know this thing called the mean value theorem. Mean value theorem says that I can rewrite this as dx dt at tj star delta t squared plus dy dt using the mean value theorem 2 times t star star j. Could be a different time for the y. So the mean value theorem says that the average, mean value theorem basically says that change in x over change in t is equal to x prime of t for appropriate t. The appropriate t has to be some time in between time j minus 1 and time j. So like here, we have both tj star and tj star star. These guys are stuck between the j plus 1th time and the jth time. This is the mean value theorem that I can find such as tj star and tj star star. But then, what do I got? Well, I got the square root of dx dt at t sub j star squared plus dy dt at t sub j star star quantity squared, and I can pull out a delta t. So, if we take the sum of j equals 1 to n of, L sub j, and take the limit as n goes to infinity, well, that is the arc length. But that's also equal to the sum, the limit as n goes to infinity of the sum j equals 1 to n of the square root of, dx dt at t sub j star quantity squared plus dy dt at t sub j star star, quantity squared delta t. That is nothing more than the Riemann integral. This is the Riemann integral of the integral from t0 to t1 of the square root of dx dt, quantity squared plus dy dt, quantity squared dt. So to calculate the arc length, which we usually call s, we just calculate this integral. That makes sense provided that our curve is parametrized by functions which are differentiable, right? I need to be able to apply the mean value theorem to select these times in between each time segment to get my average rate of change is given by the instantaneous rate of change. If I can't do that, this derivation breaks down, but there you go. That is how we calculate the arc length of a parametrized curve. Of course, I could just cheat. I could cheat and do this. I could go, well, you just take a little line segment like this, right? And so this is what ds is. And if you look at it, well, this should really just be dy, and this should be dx. So ds squared is dx squared plus dy squared, right? And then if you just multiply and divide by dt squared and integrate, you get that. It's cheating. But yeah. Anyway, I think I'm over time, so I'll shut up. We will actually calculate these tomorrow, and it will be glorious, right? No? Yes? No? All right. I think I also owe you guys how to calculate second derivatives in parametrics. I always forget. I'll try to discuss that at some point.